Alrighty guys, here we go with lesson 3.14, part A. Here we're talking about graphing polar functions. We talked in lesson 3.13 about polar functions or equations, polar equations being equations written in terms of r and theta. We talked about how to move back and forth between polar and rectangular forms, but today we're going to talk about how to graph these polar equations on a polar coordinate plane. So let's start by doing some point plotting, just building a table of values. So instead of x and y here, our input value is theta, our output value is the radius. So input the angle, get out the radius at that angle. I'll say that point plotting is not the method that we're going to use for making all of these graphs. We're gonna point plot a little bit here as we explore, and then for a lot of these graphs we'll find that there is a better method for us to be able to find these values. Sometimes we'll still have to do point plotting, but a lot of the time we'll be able to look at the equation and understand what kind of graph it means and go straight to the graph. So let's start by exploring r equals 4 sine theta. So we've got some selected values of theta here. Let's plug them in. So if theta equals 0, the radius is 4 times the sine of 0. Or 4 times the sine at angle 0 radians is 0. So 4 times 0, 0. So at the angle theta, I have a radius, at the angle 0, I have a radius of 0. Angle 0 right here, I have a radius of 0. That's the pole. Now, when theta equals pi over 6, r equals 4 times the sine of pi over 6. That's 4 times the sine at pi over 6 is 1/2. That gives me 2. Ooh, yuck. Do you see how this coordinate plane is not really divided into the same increments we normally do? Right here in the middle of the coordinate plane is pi over 4, but then this is pi over 8, and here 3 pi over 8. So we're not going to be right on this angle for pi over 6. We're going to be a little bit closer to pi over 4 than we would be otherwise. But here I'm going to go at a measure of 2 radians. So here on our angle out 1, 2, a little bit closer than where this value actually is. Now at pi over 3, I have 4 times the sine of pi over 3. That was an ugly 3. 4 times the square root of 3 over 2. And if I grabbed my calculator and evaluated, 4 square roots of 3 over 2 is 2 square roots of 3, which is approximately 3.46. So at pi over 3, which is going to be a little bit closer to pi over 4 than this guy is right here. Again, I don't love that this polar plane is split up the way that it is because pi over 8 are not increments that we know mostly. All right, so let's see, 3.46 out 1, 2, 3, and about 1/2. Again, not quite on this angle because that's 3 pi over 8. I'm going to be about here. All right, at pi over 2, I have 4 times the sine at pi over 2, or 4 times 1 gives me 4. And then 4 times the sine at 2 pi over 3, that's 4 times the square root of 3 over 2, which again is 2 square roots of 3, or about 3.46. So 2 pi over 3, maybe a little bit closer, so not this first one, but a little bit closer to pi over 4 than that measure there. Out 1, 2, 3, and close to 1/2. And then at 5 pi over 6, I have 4 times the sine of 5 pi over 6, or 4 times 1/2 gives me 2. So in the angle 5 pi over 6 out here, I'm going to be out 1, 2 radians. Again, that isn't right here. It's kind of like there. And then at pi, I have 4 times the sine of pi, or 4 times sine at pi is 0, I get 0. So right here on pi, I have 0 radians, which is the pole. So I went from this point to this point, here, 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 and then right back to the pole. What we have made is a circle. So we're not going to point plot normally when we have a circle. A circle results when we have an equation that looks like r equals a value, a constant, times sine theta, or r equals a value times cosine theta. These are both circles. This r value, 4, notice the diameter of my circle, 1, 2, 3, 4. That measure is the diameter. Notice where that circle is located. It is oriented over the vertical axis, or a y. In polar graphing, we refer to this line as this angle or this axis as theta equals pi over 2. That's the angle measure there. So it's oriented over the vertical axis. That's because it's a sine equation. This tells me it's oriented over the vertical axis. But how do I know that it went up here, not down here? How come it's not a circle down here? That's because this constant value out in front is positive. Because 4 is greater than 0, it's oriented over the positive side of the axis. Okay, so now, having talked about those skills, instead of doing the table of values here, let's think about how this next equation would be directly graphed, knowing the things we've been talking about here. So this one was sine. It made my circle oriented over the vertical axis. This is a cosine. Cosine is associated with x's, right? Sine is associated with y's. Cosine is associated with x's. So this one's going to be over the horizontal axis. It's going to be hovering over this one here. Its diameter is 3, but it's oriented over the negative side of that horizontal axis. Horizontal axis, x-axis in rectangular, we call it in polar the polar axis. We talked about that in the last lesson. So the negative side of the polar axis, or x-axis or horizontal axis, because cosines are horizontal. So I'm going to start at the pole. I'm going to make a circle over here. Oh, nope, over here on the negative side with a diameter of 3. So I'm going to go out 1, 2, 3. There's the edge of my circle, and then I'm going to try to make as round a shape as I can. You'll notice in this lesson that my graphs are all a little bit lumpier than they should be, and I missed the mark a little bit here. It should have gone exactly through that point, but you will do a much better job than I do graphing. These are not easy graphs to make by hand, so we will forgive each other for not having very round shapes where we should. Okay, so if a polar equation involves only r equals a sine theta or r equals a cosine theta, your graph will be a circle. Can we describe the direction? Well, if we have r equals either a positive or a negative a times the sine of theta, then we're working vertically. If the a is positive, then our graph will be up above the pole, like this one here. Positive a for a sine graph went above the pole. If that a value here had been negative, we would still be on that vertical axis, but down below the pole. So if we have a negative a, we would go down. If our equation looks like r equals plus or minus a times the cosine of theta, that cosine tells me we're oriented over the horizontal axis. If my a value is positive, it's over here on the positive side of the horizontal axis. If my a is negative, we're over here on the negative side of the axis. So if a is positive, we're moving over to the right side of the pole. If a is negative, then we are on the left side of the pole. What similarities do those graphs have? Well, they are both circles. They both touch the pole. They both pass through the pole. They both have similarity, they both have symmetry along an axis. So these are circles that pass through the pole. They both have axis symmetry. Which axis depends on whether it is a sine or a cosine. What are the differences? Well, some of them were vertically oriented, some of them are horizontally oriented over the vertical axis or the horizontal axis. How do we know from the equation? Well, we've been talking already about the idea that that comes from the sine or the cosine. If we have a sine equation, then we are oriented over the y-axis. We have y-axis symmetry. In polar world, we should call that theta equals pi over 2 symmetry instead of the y-axis. If we have a cosine, that's horizontal, so it has x-axis symmetry. Or x-axis in polar world is called the polar axis. Last question here. Give the ordered pair r theta of the point that is farthest away from the pole or the origin. How is this related to the equation? So in the equation r equals 4 sine theta, that 4 gave us our diameter. So the furthest point away from the pole in that graph was the point at the angle pi over 2 with the radius, keep in mind not the radius of this circle, but r as in how far I measure from the pole along this angle, 4. So the point r comma theta was 4 comma pi over 2. So that 4 came from the diameter, being this a value, and pi over 2 is the angle measure where sine has its maximum. In the other equation, the second equation from part B up there, we had r equals -3 cosine theta. The furthest point away from the pole in this problem was -3 was my r value. Oh no, actually, let me say this is angle theta. I was thinking for a second in rectangular, this would be an x value -3. But in polar form, we are along the angle pi at a radius of 3. We are at an angle pi, whoops, radius comes first, huh? Angle pi, radius 3, angle pi. Or we could also think of this point as the angle 0 with a negative radius. Work backwards from the angle, negative radius 3. So we could also think of it as angle 0 with a negative radius on the opposite side of the circle. So this 3 or -3, depending on which way we wrote it, indicates the diameter. Think also pi or 0, that is where this cosine curve, where cosine function in general has its maximum or minimum value at the angle 0 or pi. All right, so if we can recognize this equation as a circle, we can just go straight into graphing, and the symmetry in this circle depends on whether we had a sine curve or our sine equation or a cosine equation. But not all graphs will be quite so clear in terms of what kind of symmetry they display. Let's talk about how we test for symmetry in polar equations. So, in order to test for, let's say to start here, we're testing this WRT. We've talked about the abbreviation WRT before. I don't usually put the slashes in here, but we've said this means with respect to. So symmetry with respect to theta equals pi over 2 is our first test. This is vertical axis symmetry, like having y-axis symmetry on a rectangular graphing system. Here's our test. We replace the r and the theta in our equation with a negative r and a negative theta, and then simplify. If what we get after simplifying is the same as the original equation, then our graph has symmetry with respect to theta equals pi over 2. It has vertical axis symmetry. That is a graph where I will see the same thing on both sides of the vertical axis. Next, our test for polar axis symmetry. Polar axis is our horizontal axis, like saying the x-axis. Here's our test. We replace the r and theta in our equation with r and negative theta. So r stays the same, change theta to a negative theta, and then simplify. And I want to ask myself, is it the same as the original equation? If so, then it has polar axis symmetry. Our third test is for pole symmetry. Remember, the pole is another name for the origin. The pole is the name for the origin in a polar graphing system. So this is just like having origin symmetry on a rectangular plane. Our test is to replace r comma theta in our equation with negative r comma theta. So change r to a negative r, but keep theta in the equation the same, and simplify. If this is the same as the original, then our equation shows pole symmetry or origin symmetry. So if I have pole symmetry, I will find that any point here has a coordinating point on the other side. Any point here has another point on the other side of just opposite it on the other side of the origin. Has a I said coordinating, but I meant corresponding point. All right, and if we have polar axis symmetry, horizontal axis symmetry, I will see that any point up here on the top half of my plane has a corresponding point on the bottom half of my plane. Here's some things that are going to be helpful to remember as we do this simplifying in our symmetry tests. We have talked, when we were learning sine and cosine and tangent graphs, we talked very briefly about which functions were even and which functions were odd. So we should remember that our even functions are cosine and its reciprocal function, secant. They're both even, which means the cosine of negative theta can simplify to the cosine of positive theta. Secant of negative theta is equivalent to the secant of positive theta. That fact will help us when we're simplifying after we plug in these negative r's and negative thetas. Our odd functions are all the rest. Only cosine and its reciprocal are even, which means the other four, sine and its reciprocal cosecant, as well as tangent and its reciprocal cotangent, they are all odd. For an odd function, when I take that trig function of a negative angle, it is the opposite of that trig function at the positive angle. So sine of negative theta is equivalent to the opposite of the sine of theta. Cosecant of negative theta is equal to the opposite of the cosecant of theta. The tangent of negative theta is equal to the opposite of the tangent of theta. And cotangent negative theta is equal to the opposite of the cotangent of theta. That'll be helpful to us when we're doing those symmetry tests. Okay, but here's the thing to know about symmetry tests in polar graphing. If this test is true, if I do this thing and I simplify and it's the same as the original equation, it definitely has this symmetry. But if it doesn't pass the test, all it tells me is that it may or may not have the symmetry. If I do the test and I can't be sure whether or not it has a symmetry, I can't use the symmetry to help me graph. But once I graph it, I may observe in that graph that it actually did have that symmetry all along. So if a graph fails a symmetry test, it doesn't mean it's not symmetric. But if it passes the test, it definitely is symmetric. So passing the test means definitely symmetric. Not passing the test means maybe, maybe not. All right. So, but in general, it is helpful to know that if we have a graph where r, the radius, is equal to some function of sine, it's going to be symmetric with respect to the vertical axis, the y-axis, or theta equals pi over 2. If our equation is r equals some function that has cosine in it, that's going to be symmetric with respect to the x-axis, or the horizontal axis, the polar axis. This makes sense. Again, sines are associated with y values and cosines are associated with x values, so that kind of symmetry should seem like it makes sense. All right, so we're going to talk about several different kinds of polar graphs. The first today is called a rose curve, because when I graph it, it's going to look a lot like a flower. So these rose curves, this looks very similar to the circle equation. The difference here is that I have a coefficient multiplied in front of the theta. So like here, 3 theta, here, 5 theta. Without that 3 or 5, it would have been, like without that 5, that would be a circle, but with a coefficient there, turns it into a rose curve. If n is an odd number, like 3 or 5, then that is the number of petals that my flower will have. If n is an odd number, there will be n petals. But if n is an even number, like if this were, we can see on the next page, here 2 theta, here 4 theta, then there are twice this many petals. This flower will have 8 petals. This flower will have 4 petals. So if n is even, there are 2 times n petals. Okay, here's another important thing to know. If n is an even number, that's not what I meant to say. Okay, let me get back to that. Let's just dig in. Okay, I know what I meant to say here. If n is even, then I will find my first petal oriented over this axis or this axis. So if n is even, one petal is oriented over an axis. So if it's a sine equation, it's going to be oriented over the y-axis, a cosine equation oriented over the x-axis. So for these rose curves, I'm going to figure out where the first petal is and then make all the other petals equidistant around the curve in comparison to that. If n is even, like in this case, if n is, this is wrong, guys. I meant to say if n is odd. I'm so sorry. If n is odd, then one petal will be oriented right over the axis indicated by the sine or cosine. And that'll tell me exactly where to start with my first petal. So here, I have an odd number, n is an odd number, so I can start right on the cosine axis, the axis indicated by cosine, which is horizontal. The first petal will be right over the horizontal axis, but which side of the horizontal axis? Well, you see how this 2 in front is positive? It indicates that I should start over the positive side of the horizontal axis. So this being a cosine function will have horizontal axis symmetry or polar axis. We might think of this as being like the x-axis, but the name in polar coordinates should be polar axis instead of x-axis. Okay, n is 3, so that's an odd number. I have exactly that many petals, 3 petals. How long are these petals? Oh, that's what this value out in front, this A, tells us. So the petal length here is 2. So over the positive side of the horizontal axis over here, I'm going to draw my first petal, length 2. there are 3 petals in total that will be equally spaced around this graph. We have 3 petals equally spaced over 2 pi radians. So then how far should I go to get to the next petal? Well, if I take those 2 pi radians and divide it up among those 3 petals, all of those petals will be 2 pi over 3 radians apart. So the tip of this petal was at 0 radians, so the next one will be at 2 pi over 3 radians, which is going to be over here. Well, again, I don't love the way this was divided. This isn't exactly 2 pi over 3, but let's pretend that it is and go out here 1, 2 in radius at that angle. And then I will go another 2 pi over 3, 2 pi over 3 plus another 2 pi over 3 brings me to 4 pi over 3, which is actually over here a little bit, not quite here, but let's pretend for the moment. 4 pi over 3. Ta-da! All right, let's look at this one now. I'm going to start with the first petal oriented over the positive side of the vertical axis, a petal with length 3. So here's my vertical axis because it's a sine, positive because that A value is positive, radius 3. I'm going to go out that far to get to the tip of my petal like this. It should actually be like a little bit rounder at the end. It shouldn't look like it's coming to a point. Okay, symmetry. Because this is a sine, a function of sine, it's going to have vertical axis symmetry, which in the polar world is called theta equals pi over 2. It's the same thing as saying the y-axis if we were talking rectangular coordinate system. Our n value is 5. Because that n value is an odd number, there are exactly n petals. Because this is odd, there are 5 petals, all 3 units long. Now, how far should I go to get to the next petal? There are 5 petals evenly spaced over 2 pi radians. So they will all be 2 pi divided by 5 radians apart. Now here's where this gets to be a little bit of a pain in the neck. Our graph is not spread out in increments of pi over 5. So this might be a little bit easier to consider if I think about degrees. So if I think about taking 360 degrees and dividing it evenly 5 ways for those 5 petals, grab my calculator, I'd find those are all 72 degrees apart. So I can think, well, this first petal is at 90 degrees. If I go 90 degrees, 72 degrees this way, so from 90 subtract 72 degrees, I should get to the next petal in this direction. 18 degrees is going to be, let's see, this is 45 degrees, so this is 22.5 degrees, so 18 degrees is going to be a little bit shy of that. So I'm going to go out a radius of 3 on 18 degrees, and then I'm going to make a petal. Let's think about where I am going this direction from the first petal. So I'm going to start at 90 degrees and add 72 degrees to get to the next petal. I'm at 162 degrees. So let's see. This is 90 degrees. This is 135 degrees. This is right in between them, 112.5 degrees. This is 180 degrees. Right in between 135 and 180, I have 157.5 degrees. I'm looking for 162. So I'm going to be a little bit further than 157. So I'm going to go out 1, 2, 3 out on the angle measure 162. And I'm going to graph that into a petal. Where will I be after another 72 degrees? I'll be at 234 degrees. So let's see, if this is 180, here is 225 degrees, here is 270 degrees. Right in between 180 and 225, here is 202.5 degrees. in between 275 and 270. I'm sorry, 225 and 270. Here's 247.5 degrees. I'm looking for 234, so it's going to be a little bit bigger than 225 in here somewhere. So I'm finding that angle. I'm going out a radius of 3 right here. Oh, hey, you know how we said this had vertical axis symmetry? So this point right here should correspond to a point at the same radius over here. This angle here should correspond to an angle over here. Why don't I just use reflection to help me out in graphing that other petal? Looking good. All right, so we said here, if n is odd, then I can put the first petal right over the axis that corresponds to that trig function. Sine, put the first petal right over the y-axis, positive side here. Here, cosine, put the first petal over the x-axis, positive because A was positive. If that had been negative, then I would have started first petal over here. But if n is even, the first petal may or may not be oriented over the axis. So if n is even, the first petal may or may not be oriented over an axis. So in this case, we have to default to point plotting. So I'm going to build a table of values here. When we do point plotting, like we did on the first page of this lesson in polar form, when we do point plotting, we input a theta value. The output is the r value. So we're going to input a theta value, output an r value. Why don't we practice some of these symmetry tests that we were talking about on the previous page? Because if I know that I have some symmetry, then I can use reflection to find some more points. So also, we need to practice these symmetry tests because this is certainly something that we could be tested on the AP exam. So let's test for symmetry with respect to theta equals pi over 2. We said our test there is to change r theta to negative r negative theta. So I'm going to take the original equation, r equals 3 cosine of 4 theta. I'm going to change r to negative r and theta to negative theta and simplify. Well, here in my argument, 4 times negative theta, that's the same thing as saying negative 4 theta. And then I think cosine is an even function. So the cosine of the angle negative 4 theta is equivalent to the cosine of the angle positive 4 theta. So negative r equals 3 cosine 4 theta. We want to compare this to the original, which had a positive r. So why don't I multiply or divide both sides by negative 1? I get r is equal to negative 3 cosine of 4 theta. That does not look like the original equation, so it did not pass this test. So this means that this graph may or may not have symmetry with respect to theta equals pi over 2. It didn't pass the test, so I can't use symmetry to help me graph, but we'll see when we get to the end whether or not it really did have this kind of symmetry. Next up, let's test for symmetry with respect to the polar axis. That's similar to the x-axis. It's the horizontal axis. Our test here is r theta, change it to r negative theta, and simplify. So the equation r equals 3 cosine of 4 theta changes to r equals 3 times the cosine of 4 times negative theta, or r equals 3 times the cosine of negative 4 theta. Because cosine is an even function, the cosine of negative 4 theta is equivalent to the cosine of positive 4 theta. This is the same as my original equation, so I can see that my graph will definitely have polar axis symmetry. So anytime I find a point down here, I can reflect it to above the horizontal axis, find a corresponding point up here. Next, let's check for symmetry with respect to the pole. Our test here was to change r theta to negative r theta. So the equation the equation r equals 3 cosine of 4 theta. I changed to r equals 3 cosine of 4 times negative theta, or r equals 3 cosine of negative 4 theta. Cosine is an even function. Look what I did. I accidentally changed theta to its opposite. I meant to do r, huh? So this was positive theta, still positive theta. I meant to change r to its opposite right here. So now if I want to compare this to the original, let's multiply or divide both sides by -1. So now r, negative r divided by -1 is positive r equals negative 3 cosine of 4 theta. This does not look like the original, so it didn't pass the test. It may or may not have symmetry with respect to the pole. The only one I can count on is symmetry with respect to the polar axis. So by testing, let's say on symmetry, it tests positive for polar axis. It may have other symmetries by the time we are done. Let's work on graphing here. So I'm going to think if n is even, then we should have 2n petals is what I meant to say. We should have 2n petals, or 2 times my n value is 4. We should have 8 petals. How long will they be? 3 units long. 3 units long. Okay. Now, I know that I have 8 petals to spread evenly around a 2 pi radian circle, so those 2 pi radians divided into 8 parts, or pi over 4 radians, to get from the tip of one petal to the tip of the next petal. Okie dokie. So let's, now we can't, because n is not odd, I can't be guaranteed that the first petal hovers over the horizontal axis. So what I have to do here is start in on that table of values. Once I find a full-length petal that I can graph in, then I will know how to spread out the rest of the petals from there. But I have to start graphing until I find a full-length petal. So let me take let me take theta values as the input value here. And r is equal to 3 cosine of 4 theta. Let's start at angle 0. R is equal to 3 times the cosine of 4 times 0, or r is equal to 3 times the cosine of 0, or 3 times the cosine of 0 is 1, so 3. Oh, I found here at the angle 0 radians, I'm going to go out 1, 2, 3 right here. That is the full length of a petal. So I have found the end of a petal. That's lucky. So from here, I'll think if the tip of this petal was at 0 radians, I move pi over 4 radians to get to the tip of the next petal right here. Oops, those shouldn't overlap. I think I need to make them a little skinnier. Pi over 4 to get to the tip of the next petal here. And then pi over 4 radians to get to the tip of the next petal here. Pi over 4 more. Then pi over 4 more. Move again, pi over 4. These all have a radius of 3. Move pi over 4 more. Radius of 3. I've got 1, 2, 3, 4, 5, 6, 7, 8. We got it. Okay. So after I have gotten that graphed and I take a look at the graph we ended up with, do you see that this certainly does have the polar axis symmetry that it tested for? Every point up here corresponds to a point down here. But notice also it has vertical axis symmetry. Every point over here corresponds to a point over here. It also has polar symmetry. Every point here corresponds to a point on the opposite side of the pole here. This point corresponds to a point on the opposite side of the pole. This point corresponds to this point on the opposite side of the pole. So it tested positive for polar axis symmetry, but it also has theta equals pi over 2 and pole symmetry. I just couldn't see them in the test. All right. Next, here we've got another rose curve, I can tell because of the coefficient in front of the theta. Because that coefficient is even, I have 2 times this many petals. N is even, I have 2 times n, or 2 times 2 petals. I've got 4 petals on this one. 2 times 2, or 4 petals. How long will they be? 4 units long. But because n is even, I'm not guaranteed that the first petal hovers over the sine y axis, the theta equals pi over 2 axis. So here, again, because n is even, I have to start by building a table of values, plug into the equation until I can find a full-length petal to plot. So I have theta values plugged into the equation. R equals 4 sine of 2 theta. Let's start at angle 0. R is equal to 4 times the sine of 2 times 0, or 4 times the sine of 0. The sine of 0 is 0, so 4 times 0, 0. At 0 radians, the angle 0 radians, my radius is 0. That means I have not left the pole. All right, let's try pi over 6. R equals 4 times the sine of 2 times pi over 6. That's 4 times the sine of 2 times pi over 6 is pi over 3. So I have 4 times sine of pi over 3 is square root of 3 over 2. That's 2 square roots of 3. If I grab my calculator, I'll find that's approximately 3.46. So I'm going to go on pi over 6. Now here's pi over 4. This is pi over 8. So pi over 6 is actually a little bit closer to pi over 4 than this pi over 8 mark. So about in here, I'm going to go out a radius of 3.46. 1, 2, 3.46 is close to a half. This means that we know that we have, because we've got a sine. Oh, guys, I forgot to test for symmetry, didn't I? Well, let me show you a quick look at it. Let's pretend we tested for symmetry together. Symmetry with respect to theta equals pi over 2. Change r theta to negative r negative theta. So here r changes to negative r. Here theta changes to negative theta. 2 times negative theta is negative 2 theta. But sine is an odd function. So the sine of negative 2 theta is the same thing as negative sine of 2 theta. Or here when I multiply by 4, I get negative 4 sine of 2 theta. Divide both sides by negative 1, r equals 4 sine theta. That's the same as the original. So I can see I definitely have symmetry with respect to theta equals pi over 2. That's the vertical axis. So if I have a point over here, I also have a point over here at that same radius, out 1, 2, 3.5 right here. That's helpful. But when I try the other 2 tests, it fails. For polar axis symmetry, I change theta to negative theta. So here theta changes to negative theta. 2 times negative theta is negative 2 theta. Now, because sine is odd, the sine of this negative angle is the same as the opposite of the sine of positive 2 theta. 4 times this negative, let's call it negative 4 sine 2 theta. But this does not look like my original equation. So we can't be guaranteed that there's polar axis symmetry. We'll see in the end that we do have symmetry, but we don't see it in the test. Likewise, for symmetry with respect to the pole, we also don't see that symmetry in the test. We change r to negative r changes to negative r, and then I solve for r, multiply or divide both sides by -1. This does not look like the original equation, so it didn't pass the test. I cannot be guaranteed that it has either of these symmetries, but I do know from the test theta equals pi over 2 symmetry. So from the test, I know it has theta equals pi over 2 symmetry. All right, back to our table of values. We have not found a full-length petal yet. Let's go now to pi over 4. So r is equal to 4 times the sine of 2 times pi over 4, or 4 times the sine of 2 times pi over 4 is pi over 2, or 4 times the sine at pi over 2 is 1, 4. Ooh, 4 is a full-length petal, right? The length of the petal here was 4. So on pi over 4, I'm going to go out 1, 2, 3, 4. So here is a full-length petal. I can see how wide the petal is right here. I know it's going to be just as wide on the other side. Here is a petal. Now, if there are 4 petals spread evenly, 4 petals spread evenly over 2 pi, the 2 pi is shared by 4 petals, then they are each, they are each pi over 2 radians apart. So from the tip of this petal at pi over 4, if I move pi over 2 radians, boop, here I am at 3 pi over 4. From 3 pi over 4, if I move pi over 2 radians, right here, out 1, 2, 3, 4. If I move pi over 2 radians, here I am at 7 pi over 4, out 1, 2, 3, 4. Okay, so after we graph, we can see it did have that theta equals pi over 2, that vertical axis symmetry that we tested positively for, but it also has horizontal axis symmetry, polar axis symmetry. I see it also has symmetry with respect to the pole. So it actually has all 3. We can observe that it also has pole and polar axis. All right, so it is a little bit of a pain in the neck when we end up having to do symmetry tests and plot points. It happens for these Rose curves with an even number of, a Rose curve with an even n value. But let's talk about some more graphs where I do not have to build tables of values. There is a category of graphs called limacon. Sometimes people pronounce it limacon, but it comes from the old French word limacon for snail. So you'll find that these limacon graphs all look vaguely like a snail if you really stretch your imagination. So limacon is a category of graphs that also contains graphs called cardioids. Limacon in general can come in many shapes, but a cardioid, as the name suggests, cardio, is kind of a heart shape. It's kind of a roundish heart. So it is, all of these graphs are going to be kind of circular in nature, but this is going to be kind of circular, but come in at a sharp point. So it's rounded like here down the bottom, but then it pulls into a very sharp point. Let's see a couple of cardioids first. All of these limacon come from equations, so limacon in general, they all come from equations that look like r equals a number plus or minus another number cosine theta, or r equals a number plus or minus a number sine theta. See the difference here between these equations and the Rose curves or the circles? These guys didn't have any addition or subtraction, no constant added or subtracted to them. These limacon all will. This ratio of A over B tells us what kind of a limacon we have. If this ratio, A over B, is equal to 1, meaning that A and B are the same number, then what we have is one of these heart-shaped cardioid graphs. You might be able to guess that whether it is sine or cosine tells us what axis it is oriented over. If it's a cosine, it's most of the graph falls over the horizontal axis. If it's sine, most of the graph falls over the vertical axis, theta equals pi over 2. If there is addition between these, most of the graph falls on the positive side of this axis. If there is a minus in between these, then most of the graph falls on the negative side of that axis. Okay, so if A equals B, or if A over B equals 1, then we have a cardioid. Let's take a look at some of these. So this one, because it is cosine, it's going to have polar axis symmetry, like x-axis symmetry. It's going to be horizontal axis symmetry. Here is my A value, here is my B value. The plus sign in between them tells me that this is oriented over the positive side of the horizontal axis. Okay, ratio, we said A over B is 2 over 2 equals 1. That means it is a cardioid. Okay, so I know that it's going to have like kind of this shape, but it's oriented over the positive side of the x-axis. So it's going to be like over here. Here's how I find how big this cardioid or heart is. This A value of 2 tells me that on not the horizontal axis where most of the body of the graph is going to be, but on the opposite axis from the pole, I should go out 2 units in each direction. On the horizontal axis where most of the body of this graph is, I find the distance to move from the pole by A plus B. A plus B, 2 plus 2, tells me I'm moving 4 units, 1, 2, 3, 4, along the axis where most of the body of our cardioid is. So this is a heart-shaped graph. It's going to kind of look circular like down here, but then it's going to go through these 2 points. It's going to pull in toward the pole, a very sharp point there at the pole. It should maybe be a little bit rounder here, but these graphs aren't easy to accurately graph by hand, so we're going to kind of fake it here. So this distance here, A plus B, this distance here, A, this distance here, A. All right, let's look at this one. Again, I have this ratio, A over B. Ignore the sign because that just tells me which side of the axis to go to, but 2 over 2, ratio A over B, 2 over 2 is equal to 1. That's when I have a cardioid. This one's going to be oriented over the vertical axis, over the sine axis, theta equals pi over 2. That minus tells me that most of the graph is going to fall down here on the negative side of this axis. The A value is 2, so not on the vertical axis where most of the body is, but on the opposite axis, I'm going to move from the pole 2 units in either direction. My graph is going to go through those points. How far down here do I go on the axis where most of my graph is oriented? That is A plus B. 2 plus 2, 4 units on this axis where my graph is oriented over. So I'm going to go round like this and as round a graph as I can through these points, and then I'm going to pull in toward the center here and pull in toward the center here. This graph has symmetry with respect to theta equals pi over 2, that vertical axis, because it was a sine. That's like having y-axis symmetry. Okay. Now, let's talk about some other kinds of limaçon. Here, our author labeled this cardioids, but the ones we will see here are not cardioids. Cardioids is a particular kind of limaçon. These are just general limaçon. Oh yeah, I spelled it right. Okay. Okay, so notice the difference here. In the previous cardioids, A over B gave us 1, but here 1 over 2 is not equal to 1. When the ratio A over B, which in this case is 1 over 2. Again, A and B are just these numbers. Ignore the sign. That just tells us which direction to go on this axis. But the number 1 over the number 2 is less than 1. So instead of having a graph that pulls in just to a sharp point here, if A over B is less than 1, then we will have what we describe as an inner loop. So we'll have, it'll look similar to a cardioid like this, but then at the tip, it's gonna loop-de-loop inside. So this graph, because it is a cosine, it should have horizontal axis symmetry. This is polar axis symmetry, like x-axis symmetry. Just like our cardioids, this A value tells me how to move to get to either side of the points that lie on the not horizontal axis, but the vertical axis. So from the pole, I'm going to go up 1 and down 1. This A value is a measurement on the axis that isn't where we're oriented. So not on the horizontal, but in this case, the vertical. I still find my way out on the axis I'm oriented on, the cosine horizontal axis. I still find the distance there by adding A plus B. A plus B, 1 plus 2 tells me to move 3 units to get kind of to the body of this graph. I want to be on the negative side of the horizontal axis. Negative side of the horizontal axis is where most of this graph lies. 1, 2, 3 out here. So I can see this graph goes like this, kind of. Pretend it went through those points, but there's an inner loop here. How long is the inner loop? The inner loop is the difference between these two values, but actually the absolute value of that. The absolute value of the difference A minus B, or the absolute value of 1 minus 2. So 1. This inner loop is going to be 1 unit long, so I'm going to go whoop through 1 unit inside. All right, let's try another. So here, sine, I know that it will have vertical axis, theta equals pi over 2 symmetry because it's a sine. The ratio A over B is 1 over 2. That is less than 1, so we're going to have an inner loop. Okay. Let's find how far to go to get to the body, kind of the big part of our graph. So that is A plus B, 1 plus 2, 3 units from the pole to get to the end of like the kind of big part of my graph. Sine, so we're vertically oriented. On the positive side, the majority of my graph is going to lie up here. So from the pole, 1, 2, 3, there's kind of the outer limit of my graph. To find how far I move to the left and right here on the axis where I'm not oriented, that is the A value. A is 1. So I'm going to move from the pole 1 unit over here and 1 unit over here. I know that this part of my graph looks kind of like this. Maybe not so lumpy, maybe more like that. And then I'm going to come around here to the pole, like we did with the cardioid, but now I'm going to have an inner loop. How big is that inner loop? The absolute value of A minus B, the difference of these two. The absolute value of 1 minus 2, the absolute value of negative 1 is 1. 1 unit long for my loop there. Okay, let's look at this next one. So here, cosine tells me I'm going to be oriented over the horizontal axis. That plus tells me I'm going to be oriented over the positive side. The bulk of my graph is going to be over here. Because of that cosine, we're going to have symmetry with respect to the polar axis. Let's look at the ratio. A over B is equal to 3 over 2. Now, if this was equal to exactly 1, it would be a cardioid. That's not it. If this was less than 1, it would have an inner loop. That's not it. This is greater than 1. Now, how much greater than 1 does make a difference here. If we have a ratio that is bigger than 1, but less than 2, then we will have what's called a dimple. So our graph is going to be, pretty round, but then instead of coming into a sharp point like a cardioid, and instead of pulling in so far that we make an inner loop, like when we had a over b is less than 1, we're just kind of like have a little dent. Let's figure out the rest of the graph here. So just as before, I think to get to the end of my graph here, the outside of my graph, we're over the cosine horizontal axis, the positive side, where the bulk of the graph lies here. To figure out how far I go out, I add a plus b. A plus b, 3 plus 2, 5 is how far I move from the pole on the horizontal axis in the positive direction to get to the end of my graph. So I'm picturing my graph like in here. Now my graph will intersect this axis where we're not oriented over at the A value. So I'm going to move from the pole up 3 here and down 3 here. I know my graph is going to look like this on that side. Now, I don't want to pull into a sharp point here like a cardioid. I don't want to pull in tight to the pole, and I don't want to pull in tight to the pole and make a loop. What I want to do is kind of approach the pole but not really get to the pole. So how close do we get to the pole here? That is the value a minus b. 3 minus 2, a minus b, 3 minus 2 is 1. So here I get 1 unit away from the pole. So we come around like this and then come into the pole and then back out. So these distances, here, a plus b. Here, a. Here, a. Here, a minus b. So just in the same way, the absolute value of a minus b told me how far I went in from the pole. In this case, it is actually out from the pole. So I'm not taking the absolute value here. So it's still a minus b, just like a minus b told me how far I was going from the pole right here. A minus b tells me how far I'm going from the pole here, but not into my limacon, but on the outside of my limacon. Alrighty, let's look at the last one here. Symmetry with respect to the vertical axis, theta equals pi over 2. I'm going to be on the negative side of that vertical axis, so I'm picturing the majority of my graph being down here. Ratio a over b is 5 over 2. If that were equal to 1, it would be a cardioid with a heart-shaped graph with a sharp that pulls in sharp to the pole. That's not it. If this were less than 1, it would be a limacon with an inner loop. It would pull in tight to the pole and then have a loop around in the center, but that's not it. It is bigger than 1, but it's not between 1 and 2, so it's not going to have a dimple. This has even less of an indentation. The bigger this ratio gets, the further out from the pole it gets. When this ratio a over b is really small, less than 1, we're so close to the pole that we wrap around and come inside. When it equals exactly 1, we pull in tight to the pole. When we are bigger than 1, then we are not pulled all the way into the pole. If we're bigger than 1, but not that big, between 1 and 2, then we're pulling to the pole here. If we are greater than or equal to 2, then we have a shape that is called convex. There is no dimple. So it looks circular. Oh, we're vertically oriented, so we're picturing it down here. So we don't come into a dimple right here. We just kind of flatten out. So it's going to look a lot like a circle, but then it doesn't get very circular up here. It looks kind of flat. Okay, so just as before, on the side where my graph is oriented, where the bulk of my graph is, I find how far to move out from the pole with a plus b. Here that's 5 plus 2. 7. From the pole, I'll be out 7 units. That's a little bit past where our graph ends. That's okay. We can manage it. So this value right here, a plus b. On the axis where I'm not oriented over, still going out a units. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this value right here, a. Now the value a minus b Just like A minus B here told me how far I was from the pole, A minus B tells me how far I am from the pole here. So 5 minus 2, or 3. I'm 3 units from the pole here. So, but I'm not gonna dimple right here like this graph did. I'm not gonna pull in toward that. I'm just gonna try to make it look like that's as far as my graph goes out, like it kind of flattens out to that value a little bit. Oops, then I missed the mark over here, didn't I? I'm trying to hit all these points. Ooh, what an ugly graph. You guys did much better on your paper, I'm sure. Let me get rid of that. So it should look like it is approaching circular, but it's not quite a circle on this side. It kind of gets flat. Okay, can we describe or explain a pattern for cardioids and Limassol curves, symmetry, intercepts, similarities, differences? Here are the things that we've talked about. If it's a sine function, then it's oriented over the vertical axis. If it's a cosine function, it's oriented over the horizontal axis. If it is A plus B, like right here, A plus B, A minus B, tells me what side of the axis I'm oriented over. A plus B, I'm oriented over the positive side of the axis. A minus B, I'm oriented over the negative side of the axis. So we're referring to how it looks in the equation. The ratio tells me what kind of Limassol it is. A over B equaling 1, that's a heart, a cardioid, pulls into a sharp point at the pole. If A over B is less than 1, then we pull in so tightly toward the pole. Think about how this is even smaller. We pull in tighter toward the pole so we get an inner loop. If A over B is big, we're further from the pole here. We don't pull in tight to the pole. We don't pull in so tight that we wrap all the way around. We're going to be less close to the pole. So it's just got a dimple here if our A over B is between 1 and 2. If A over B is greater than or equal to 2, then it's convex, where it looks kind of like a circle, but flattens out a little bit in the middle. You'll see that in the very back page of this lesson, our author summarizes these polar graphs for us. She writes circles a little bit differently. She says these look like 2a sine theta, where the radius is a, but what we said was that it looks like r equals a sine theta, where a equals the diameter. Those mean the same thing, but this is how we talked about it earlier. Here, cardioids, a over b equals 1. Here, other Limassol, convex Limassol, if a over b is between 0 and 1, we've got a little dimple. If a over b is bigger than, greater than, or equal to 2, then we have something convex that doesn't have a dimple. If a over b is less than 1, then we have an inner loop. And those rose curves, they look like circles equations, only we have an n value here. If n is even, we have, oh, that was backwards, hold on. If n is odd, then we have n petals. If n is even, then we have 2 times n petals. Now we've got it right. Okay, guys, come on back and we'll do part B.